Good morning, everybody. Can you hear me?
Yes.
Yes. It would be great if you could turn on your camera so you can you can see me and I can also see someone to talk to. How's it going?
Good.
Prepping for the exam, I reckon. So I'm hearing some anxiety about the exam. Is that correct?
Actually, I have a question if you don't mind about the exam.
Of course.
I have I have highlighted in my book and I also wrote in my book. Will that
Mm-hmm.
be a problem for the exam?
Yeah, so there's a lot of these kinds of questions about what is allowed and what is not allowed. So we're gonna write down a list in the on Canvas what is allowed, but these this basic stuff just marking in your book, it's just not a problem. So if the main thing for us is that you show us that you are able to do these tasks that we train you to do, so you we'll get to our learning goals essentially, and one of the most important things in that task is that you do it alone and don't communicate with others. So if you have something written down in your book or highlighted, that's absolutely not a problem. There were some questions on, can I use other programs like Excel? Well, I don't think that is smart because we train you to use R and we train you to use SPSS. So those are our learning goals. So we would rather see you have use those applications where we actually train you for instead of going a different route. And I also understand that there's some anxiety about we're going to be using Proctorio as a proctoring software, and I get the feeling that there's this notion that that this Proctorio software, that this software, that this proctoring software will determine if you if the software will determine if the behavior is allowed or is not allowed, but that's absolutely not the case. The software registers. It has some flagging based on looking to the other side, but in the end, the examiner, that's me and Roland, and the exam committee is in between this. So if you look the other way because you're thinking, what would the answer be? That's not going to be a problem. So try it's the software is not going to decide for us. We're still in control. So that's some reassuring thoughts on that. I hope that helps. Does it?
Yes, thank you.
Okay. So yeah, you just go into the exam. You follow the instructions. Try your best to do the questions that we throw at you, and well, these are not gonna be questions that are gonna come out of the blue, because we're gonna ask questions in line of what we've been training you for, and what we've been preparing you for. So if you look at the weekly assignments, you're gonna be asked some questions on how to compute something or how to make a graph for something, and we've been doing t-tests, so we'll probably ask you to perform a t-test in R, to calculate the t-value in R for something, or interpret some results in SPSS. So it's all in line in line with what we've been teaching you. So it's not going to be a very big surprise in that sense. Does that make sense?
Yes.
So the question I also see in the chat. So you are allowed to look at your book? Yes, of course. This is how you do the exam. How you would do the exam if you would come to an exam hall. So people, when you, well, in the exam hall we had a digital version of the book. But if you're sitting at home and you have your book beside you, yes, of course you can look in your book. So
I personally have some problems with SPSS, especially with the merging, and I also noticed that some other people that also have a Mac like Apple,
Mm-hmm.
also had problems merging documents. Will
Mm-hmm.
that be a part of the exam too?
I cannot say. So,
Like, do you know what I could do about it? Because I also sent an email to you and Roland last week, but I didn't get anything back.
no, we've been talking about getting some additional one-time support for SPSS. So we'll be coming back to that. I think through the tutorials. I'm using a Mac myself, and it works. So it is probably having to see how it works with someone else, but I'll take it into consideration. At least on
Yeah, I did discuss it with a few people that
okay.
know how SPSS
Yeah.
works, and they think it's my computer, but I don't know what
Yeah,
to do.
I see in the chat it's because of the newest Mac update. I personally on the Mac have SPSS 27 running because I'm running Catalina, and every SPSS prior to 27 just crashed on my system, so I just have the latest version. So this might be a thing. So yeah, so we're gonna see if we could provide one more session on SPSS, but we'll get back to that through the through the tutorials. So the main point that I want to drive home is that you can just go into the exam, try to be relaxed. It's not that the system is not going to determine for you. Just use your book. Just if you just do what you normally do in an exam, it's not a problem. Um, so yeah, try to relax about it.
So,
Roland said they just have to chillax.
sorry, somebody in the chat is asking, what about the PDF version of the book? Are we allowed to use that one as well, or only
Yeah,
the
of
physical
course.
book?
Of course. If you have the PDF version of the book, you can use that one, of course.
Okay,
Yeah.
thank you.
Yeah. So everything that is in line with the things that you would normally need for doing this exam, it's allowed. It's no problem. It's the things that would not be allowed in a normal exam. That's those which are the problems. If you have your app group running on your phone and those kinds of thing, or chatting in a different session, that's of course not allowed. But that's the obvious thing, right?
Could I ask one more thing?
Mm-hmm.
I feel like everyone had some time management issues with the weekly assignment. They were quite lengthy. From your experience, do you think that we have enough time during the exam to do the exercises? Will they be shorter?
Yeah, you absolutely have enough time. We've been doing this course for, well, I think it's 6 years now. No, even longer. Yeah, 7 years. So we've calibrated the time needed for the exam. So the way the exam is structured is that there will be some questions about the reasoning part and the statistics part, and Roland will elaborate on the reasoning part. But for the statistics parts, there are a few sections, in the sense that you'll have some questions on being on test selection, so which test is needed by, and we will describe some research design. We'll have some conceptual questions on statistics. We'll have some questions on performing an analysis in SPSS. We'll have some questions on calculating a test statistic in R and interpreting results, and those kinds of categories will be used in this exam. And also the coming exams, it will be structured in the same way, these kinds of categories. So it's about, for the statistics parts, 2 questions per category or something. And the difference between the weekly assignments and the exam is that the weekly assignments, they the items are how do you say, dependent on each other. So you have to answer one question, and then the next question follows up on the previous question, and you have to go through the whole assignment, which gets you from A to B, which also incorporates some explanations in the form of YouTube channels, and in the form of the YouTube knowledge clips that we put in there. The exam will be just one independent question. Perform an independent sample t-test for this experiment. What is the t-value, or something like that, or based on this research design, the researcher finds these results. What can you conclude? Wow, something like those. So the questions are independent on each other, and the time needed is calibrated to what is feasible in 2 hours. The thing is though that it's an open book exam, so you can have your book available, but it's a bit of a trap for you, because you don't you might be tempted to think, oh, it's an open book exam, I don't have to prepare that hard because I can look it up. And if you go that route, the looking up will take a lot of time. So it's absolutely better to prepare yourself well on the topics that we've covered, so that you at least know the analysis by heart to run it, yeah. So make sure you prepare yourself well. Does that make sense?
Yes, thank you very much. That was very helpful.
I see another question. Can we use quick search in the PDF? Yeah, it's same as looking up the bookmarks. So yeah, of course. These questions, I understand these questions, but they're it's logical, right? You do these things to answer the question. So it's absolutely no issue. It's the stuff that is not the stuff that when you're not making your exam alone, which is problematic. So yeah, relax, just relax. Okay, is this good?
Yeah.
Okay, we're here. So for today we have prepared the paired and independent sample t-test. So also in giving you some reassurance, this stuff you had last year. So we've talked about the independent and the sampled independent and the paired sample t-test in our previous statistics course. We're gonna run it again just to put it in perspective to the null hypothesis testing, and also as an introduction to R. On applying calculations in R to familiarize yourself with the use of R, which we'll be using in the rest of the course. So it's gradually introducing you to some new software, and also using SPSS, which you haven't used for doing these analyses. So that's what we're going to do. And we're going to start with the paired sample t-test. And so we're diving in. Let's go. So the paired sample t-test, what is it used for, you think? Anyone?
For dependent samples.
Who agrees with this?
Question, paired sample t-test is the opposite of independent t-test.
That's right.
Yeah,
yeah, but the thing is, what is opposite then in this sense?
Is it the sample group that for the paired t-test you have the same sample for both tests but a different test?
That's correct. That's correct. And maybe you could elaborate, or someone else could help you. What is meant with the same sample?
Subjects are measured twice.
Yes, exactly. That's the thing that we're talking about when we're talking about a pair. So you have one subject, one person, for example, and you do a pre-test and a post-test or something, or so it's always within the same person that you have repeated measures in that sense. But it is limited. It's just limited to one pair. So it's always only two repeated measures and no more, because that's what the paired sample t-test can do, and it's limited to that and not more. So that is exactly what the paired sample t-test is used for. So what is the contrast, for example, with the one sample t-test that we used earlier?
The one sample is only one measurement, while the paired sample are two measurements.
That's true. And what are you comparing to? So, because when you're saying we do the paired sample t-test, then it's obvious that you want to know if there's a difference between the pre-test and the post-test. But with the one sample t-test, what's happening there?
Well,
Yeah,
No,
go
go
ahead.
ahead.
well, with the one sample t-test, you're comparing one measurement to the population mean. And with the paired samples t-test, you're looking at whether there's a difference of the means of the pre-test and of the post-test.
Yes, very good indeed. That's exactly the difference where we use this, the difference between these two tests. So the one sample t-test indeed is just for, you have one sample and you specify something that you want to test it against, where you could say that that's the population mean, as you stated, but you have to realize you can put in something else too if you want. If you just want to test against a specific value, you could use the one sample t-test for that also. But now if you look at this formula, and see how so this is the way that the t is calculated based on the paired sample t-test. And so what is going on here? Do you see any similarities? Please voice them.
The standard error?
We use again the standard error, that's true. So going with, it's still a t-test, so it means it applies the same fundamental, the same trick that Cosette realized, that by dividing by the standard error makes it possible to, at least for small samples, have a more accurate estimation of the probability. So the standard error is still the same. What more?
They substitute.
Go ahead. Normally I would point at someone in the lecture hall, so yeah, you go ahead, but now I don't know who's talking, so go ahead.
They substituted the deviation, or in the normal, in the one sample t-test, you would use the difference of the mean of the sample and the population mean, but here they substituted that for the deviation of the two samples with each other.
Yeah, absolutely. So where you normally at the one sample t-test would say this d would be would be an x, would be with a bar over it, so it would be the mean of the sample, and you would subtract the population mean mu, and they the difference is now that we're not using x but we're using d. So what is this d? Where does it come from?
The difference of error.
It's of course, yeah.
So,
So
for each, oh, yeah, for each person, like the difference between the control and the treatment. I think.
exactly. So you subtract the difference between your pre-test and your post-test, and you're left with essentially a new vector, and we call this vector D, and that's the difference score. So, and if we calculate the mean of that vector, then we can, well, then we would, what would be the assumption for the null for D?
That there's no difference.
Exactly. So in essence, we're doing exactly the same thing as the one sample t-test. We're creating one vector, but in this case, it's the difference scores, and we're using that single vector to test against mu, where you would conclude that there is no, or where you would assume based on the null hypothesis that there would not be a difference. So you have the mu specified as being null, and you test this in the same way as you test the one sample t-test. Yeah, the question is, why would you? I see in the chat, and I would really like, if you're not able to turn on your mic, but for the rest that can, please look at the chat and voice the questions, so that works better for me. So the question is, why would you put if it's 0, why would you put it in there? Because you essentially don't need it. That's absolutely the case. So we put it in there to get a conceptual understanding of what is going on. So you always, and if you look at the formula that Field uses at some points, he leaves out the mu, which makes it look as if this is a special kind of t-value for that sense. Well, while if we leave it in and you see what's happening here, then you can see the similarities of what we saw in the last lecture. So that's why we just put it in there, to have a more thorough notion on what's going on.
I have a question about this.
Yeah.
Because when I saw the formula, I was actually thinking that the difference in the null hypothesis would be 0, right? Because you're stating that there's actually no difference between the pre-test and the post-test.
Exactly.
And that the mu can be about any value, because let's say that the mean, I don't know, depression of a population is, it's called 7. But then with this pre-test and this post-test, you just notice that there's no difference at all. It's still 7. So why is the mu actually 0 and not the D?
Because you're assuming the null. You're assuming that there's no difference. So
yeah.
If your pretest is some, let's say for example you have intelligence scores on the pretest and the post-test, and you do something in between which you think will have some effect.
Yeah.
Your null assumption would be that there would be no effect. So for example, if you would have an intelligence score of 120 and the treatment that you got would not help, it would still be 120. So the difference between 120 and 120 would be 0. So if that is the assumption for the null, that is the thing you would test against. But it could be that if you don't want to test against the null but want to test against some alternative hypothesis, you could specify something else in here. But that's not what's being done in mainstream in the mainstream name and Pearson paradigm.
So in that case, the D would be 0, right? And the mu would be 120.
No, the D is your data.
Oh. Okay.
And if you put your 120 in mu, then you're looking at the difference score. So you're looking at the difference between 120 and 120, and that's 0. So.
Okay.
Yeah.
Okay.
I think the confusion, if I could understand it correctly, is that the mu usually represents the mean of the population, and now it represents the mean difference.
Exactly.
Oh, okay. Okay.
That's exactly the point.
Yeah.
Yeah.
Thank you.
Cool. Okay. Thanks for clearing that up. So, our assumption, and this is a good follow-up, because we can think about the hypothesis, the null hypothesis and an alternative hypothesis for this paired sample t-test, where we could say, well, the mean difference would be equal to mu for that difference, where we would assume mu to be 0, and we can determine some alternative hypothesis, either two-sided, where we just say, well, this difference is not equal to 0, or it's higher or it's lower. And this is just one approach of specifying the hypothesis. So can you think of any other way you could write this down? So instead of using a d bar is equal to mu for d, can you think of something else that you could write down here?
Sorry. D bar equals 0.
D bar equals 0, exactly. You could say that. What more? There are more options. So that's a good one.
You could write down a sentence.
Of course. Yeah, in words, of course. And if you're not okay, we'll keep on going. Anyone else?
You could also write down the parameters of each sample and compare them to one another, I think. I think that's what we did last year during first year statistics.
Yeah, so what would you do then?
You write down the mean of each. I think it's also denoted as mu 1 and 2. I'm not sure. And then if they're equal, that's the null hypothesis. And if one is bigger than the other, you've got an alternative, and so on.
Yeah. So you'd essentially state that the mean of your one sample would be equal to the mean of the other sample.
Yeah.
That's also good. There are even more options.
Is it possible to say d1 minus d2 equals 0?
D1 minus D2 equals, I would say the mean of no, but D is defined as the difference score, so that you don't have a D1 and a D2, because D essentially is the difference. So in that sense, you could say that the mean of x minus the mean of x1 minus the mean of x2 is equal to 0. So you could say that.
Right.
Sure.
Yeah. That makes sense.
What more? I'll give you a quick primer. We're doing a t-test.
T1 is equal to T2.
T1 is equal to T2. Is there anyone that disagrees? We only get one t-value, right? Because we calculate based on the difference, the assumed mu of 0 divided by the standard error. It results in one t-value. So I see it in the chat. We could state that the t-value itself will be 0. Does that make sense?
No, please.
So if you assume that your mean difference score will be 0, so this will be 0, the D, your mu will be 0, 0 minus 0 divided by the standard error will be 0. So the results of this formula, if everything is 0, will result in a t-value that's also 0. So instead of saying the difference score is 0, you could also state our t-value is equal to 0.
Okay.
And in that same line, you could say for an alternative hypothesis, the t-value is not 0, or the t-value is higher than 0 or lower than 0. So it goes in the same line of reasoning. Yeah? Cool. So what is also good in your conceptual understanding of the different types of tests that we are performing is to have a bit of a mental representation of how that would look like in your in SPSS. So for example, if I'm thinking about the one sample t-test, I know in SPSS what that looks like. It's just one column with numbers, and I can test against something. And that also holds for the paired sample t-test. And my mental representation of the paired sample t-test in SPSS is that I would have a pre-test, K1, and a post-test, and I call it K2 here, and that these will be the data for each cell in that sense. So I know what it looks like, and knowing what it looks like in SPSS gives you some conceptual understanding of also what kinds of, if you relate what it looks like in SPSS to the kinds of tests that you would have, then that will further cement your knowledge on which statistical test goes with what experimental design, for example. Does that make sense to you?
Yes.
So the structure for the very good. So the structure for the t-test would be at least it would be two repeated measures. So each row represents one observation, and this column represents. What does the column represent? What does it represent?
The column is from the top to bottom, right?
Exactly.
So that would be all the scores on the first measurement.
Exactly.
And then the second column would be all the scores on the second measurement.
That's good. But now in terms of dependent and independent variables, what do we have then? What is dependent? What is independent? What are...
I think K1 would be independent and K2 would be dependent.
I'm hearing K1 would be independent and K2 would be dependent. Who agrees? Who disagrees?
Yeah, I don't know, but shouldn't both be dependent variables, and the independent one should be what we use to influence both the scores, both the set of scores?
Yes, so the D's from the data, I've written it down here, are the things that you the data that you actually measure. So if we're talking about intelligence scores, in both columns you have the intelligence scores. So that is your dependent variable, the thing that you measure. So your independent variable, and this is a tricky one. The independent variable is, as you said, and that's right indeed, it's essentially the manipulation that you applied. So if you would test the independent samples, for example, you would say, well, I've one group and I have the other group, and in this sense, it also the columns relate to that same grouping. I have one group and I have the other group, but it's the same person in this case. So you have one measure and the other measure. So in essence, it's the level of the independent variable. So where you would say, for example, for independent measures, which we will come to, that you would have gender as an independent variable, which has two levels, namely being either male or female, versus this situation where you would have the independent variable, which you would call time, which will have level pre-test and post-test or something. Or, well, you can think of any name that you would want to apply to your independent variable. I don't really care about that, but what you do have to realize is that the columns represents the levels that you have, the two levels that you have within that independent variable. Does that make sense?
Yeah.
Yes.
Okay.
There's a question in the chat from Britt. Are there independent variables always categorical for a paired t-test?
Yes, and that's absolutely the case. So it's always, and it's very specific, it's always two categories. So for example, if you would have K1, K2, and K3, so you have a pre-test, a middle test, and a post-test, you can't apply it a paired sample t-test because it only has two levels. And that's what I mean, that if you have a mental relation, a mental visualization of how that looks in SPSS. So for if I visualize, well, I have 3 columns, okay, then the t-test doesn't apply. So which test does apply in that case? And we'll be going into that into this course, so you will get all of them. But indeed, it's always categorical. So go into field and study the test selection scheme some advice on the test selection scheme, because what you're mostly doing is going from left to right if you follow the scheme. So you determine, oh, I have one dependent variable which is continuous, and then I have my independent variable, which I have 2, which are categorical, and which end you up with doing a t-test. But you can also run through it the other way around. So start at the independent sample t-test, the paired sample t-test, and then run backward to see, oh, what is related to the paired sample t-test, to get a notion. And what also helps in preparing yourself for the exam is try to think of some experiments that would relate to such paired sample t-test. So, okay, very good. That this makes sense.
Hi, can I ask a question?
Of course.
So K1 and K2, they're one independent variable with 2 levels, right?
Exactly.
Always the case.
Yeah.
2 levels with 1 independent variable.
Yeah.
Okay, thank you.
Yeah. So we're gonna do a data example, and we're gonna do this based on the experiment that, not the experiment, but the thing that we did in last lecture, where I asked you to look each other deep in your pixelated eyes and give us an estimation of the intelligence of yourself and the intelligence of the person next to you. And we didn't really have time to apply it during the lecture, during time because of time constraints, but we had the data from last year. And I also saw that a few of you did fill it in, so there's some data from you in this sample. So the structure of that same thing is essentially you have 1 column and you have 2 columns, and you could look at the difference. So it's the same structure as a paired sample t-test. So we could run a paired sample t-test to do this. Now sorry, I'm not showing you the data. So the structure has the IQ next to you. So you observe as a person, make an estimation of your own intelligence and an estimation of the intelligence of the person sitting next to you. So data-wise, it's the same structure, right, as the paired sample t-test. The thing is that, so it is not really a pre-test and a post-test. It's not that we measure you on one a dependent variable, have some treatment, and then measure you on a different, on the same dependent variable and compare this. So but the data structure still looks the same. So we could easily apply a paired sample t-test. So what would this represent? I actually don't know, but what do you think that this would represent? Not in statistical terms, but what are we measuring here? Anyone?
Maybe the difference how people estimate their own IQ versus how they estimate the person next to them.
That's exactly what we're doing. But what would that, in a psychological sense, what would that represent?
If people were to overestimate their own IQ, maybe?
Exactly, yeah. Or the other way around. Because you can also underestimate your own IQ, or overestimate others, or yeah, we're getting there. I heard someone wanted to say something.
Self-estimation compared to others.
Exactly, self-estimation. Should we even go so far as to call this narcissism? A narcissism scale, which can go to one side where you're very narcissistic and go to the other side where you're not? I don't know. It's a fun example.
Quick question. Would you be able to say with this exact example you're giving that you're still talking about dependent variables? That they're still dependent?
Yeah, that's a good question. So in this example, is it still actually a dependent a variable? Because it's not this. It's not really the same thing, right?
Yeah.
So I get your. I also have this that I'm sketchy about this. Structure. Well, you could reason that it's an estimation of IQ. That's our dependent variable. It's not actually the measure of IQ. But it's your personal estimation of IQ. So you could follow that line of reasoning, but yeah, it's a good point. Okay. So if we look at this, and I find these results very, very interesting to see that, for example, number 3, this one. So you're thinking, well, I am 125, but I'm looking at the person next to me, and yeah, that's absolutely one IQ point lower than me. So I find that an interesting result. Do we have some more extremes here? Here we have some underestimation of oneself. Do we have some people in here who really, really, really think they're smart? Not really. So I think we're good on the narcissism in this sample, maybe. Okay, we'll use this example to actually calculate, to go through the calculations. You saw one with 136, right? Yeah. And what did that one? This is 135. Oh, but he even thinks that is the one he's looking at is even smart. So that's interesting. Yeah.
So the dependent variable would be estimation of IQ.
Yeah.
And what would the independent variable be?
Yeah. What would you think? So it at least it has 2 levels. It has the IQ for the other person and the IQ for yourself. So how would you? That's a difficult question, right? In this case.
Yeah.
Maybe the placement in the room.
Oh, that would be. Anyone else? I don't know the answer to this. But it raises good questions. So, anyone?
It could be some underlying construct like self-esteem or narcissism or literally anything else because we don't know exactly.
Yeah, so you could make it into a narcissism estimation, well, ish. Yeah, it's a hard example, but it's good to see that it's a hard example. So to understand that you can go from something as simple as it's a paired sample t-test where we have a pre-test and a post-test, obvious, to see that you could use data in ways where a paired sample t-test obviously fits, but the conceptual understanding of what is actually going on and what we're doing is a bit hard to see. So that's very good, very good. Okay. We will not dive into this and what the absolute fundamental meaning is of this score, but let's keep it at that. Okay. Yeah. So if we want to apply the paired sample t-test, what we do essentially is calculate a difference score. So the difference between the one measure and the other measure. I call this D to get us into the setting of eventually calculating the mean of the different scores. So here we see those differences in IQ points, and so one thing to realize is that it's an arbitrary choice to say that you would subtract the second column from the first one. You could do it the other way around, right? So, and if SPSS runs this analysis, or you run it in R, no, mainly if you run it in SPSS, you don't know if it subtracts one from the other or the other way around. So it's always important when you do this analysis in SPSS to look at the actual means. And which group is associated with this, because otherwise you're not seeing the direction of the interpretation. So that's important to take notice. So you also see by at least calculating these different scores that the extremes will show themselves fairly easily. So we have this difference of this is a complete underestimation. Yeah, 22 difference, also an underestimation. Okay. So we have the different scores. And so the question that I see in the chat, can't you see it in the layout? Probably, but it might not just be the layout. It might also be that the order in which you assign your variables in SPSS could influence which subtracts from what. So you just have to be cautious about it and make sure that you actually look at the means in your SPSS output. Okay. So to calculate the mean of the different scores is essentially applying the mean function to the vector of D. I had a question in a previous lecture. I think I saw it in the chat about what is a vector. A vector is just a row of numbers or a set of numbers. So if I'm talking about the vector of D, I mean all the numbers that fall under D. So all these numbers. So the vector of D is here in R, and I calculate the mean for that one. So if I do that, I find a mean of 1.9. And I also need the sample size, so I also want to know the length of D. So in essence, these steps are exactly the same as you would do with the one sample t-test. You calculate a mean of your observations, of your scores. In this case, those scores are different scores, but the rest is essentially quite the same. So to go through the final step, we need to apply the formula to get to the actual t-value. Because of the t-value, we know what the distribution is, assuming that the null is true. So we set our mu to be 0 here. We calculate the standard deviation, so it's the standard deviation of D. but we actually need the standard error. So to get to the standard error, we need to divide the standard deviation by the square root of n. So we apply the square root of n, and we have the standard error for this one. The final step, the final piece of the puzzle that we need is we need to determine the degrees of freedom, and we need to have those degrees of freedom to determine what the shape of the t-distribution is looks like. So we've discussed in our previous lecture that for a low sample size, the tails of the t-distribution are fatter, and we need the degrees of freedom as an input for our t-distribution to know how it looks like. So with all these pieces of information, we have enough to calculate our t-value. So our t-value is actually the mean of d minus mu, which is 0, divided by the standard error of d. And that leaves us with a t-value of 1.915. Do you think that this is a significant t-value? Sorry, 1.915, yeah. Do you think that 1.915 is significant?
No.
Probably not.
Who thinks it is significant?
Maybe because it's two-sided, yes.
Maybe because it's two-sided. Could be. And what would be the result if it was two-sided? That I would put it on the right side and
the alpha will be smaller on different sides.
Exactly, that's true. Yeah. So, what would this be? This alpha, if you would choose for an alpha of 5% at both sides.
Well, it would still be 5%, but on the one side you would have 0.025, right?
Yeah, so it would be 2.5% on one side and 2.5% on the other side. Yeah, exactly. So you're making a good point in the sense that determining if this 1.9 would be significant, it's a different story if you test one-sided versus two-sided, because the critical values that an alpha one-sided of 5% would yield. So the critical value that would yield is a different critical value than when you would test on both sides, 2.5% on one side and the other side. So the position of the critical value would change. That's absolutely true.
But then it would be rather significant with a one-sided test than it would be if it's two-sided.
Yeah, I just realized that as well.
That's true. That's true. Yeah. So the thing is that you so we looked at for example I think last lecture we looked at a t-value of 2, and if that would be significant or not, and if you would assume it to be significant, that was a hard question because it was near the line of near a critical value for one-sided tests, where the critical value would be if you would choose an alpha of 5%. So it's hard to say because it's close, but it's smaller than 2. So if you have the notion of this, what this t-distribution looks like, so it's the mean of the t is 0. It has standard deviation steps of 1, and at 4 standard deviations, the curve flattens out mostly. So you know that you can have an intuition on at least that a t-value of 1 is absolutely not significant because it's something that's within one standard deviation, so it happens quite a lot. So we'll test this, of course. So we have to go from this t-value to actually getting the associated probability of finding this t-value or more extreme under the assumption that the null is true. So what I think you did in previous years, I already mentioned, was use a lookup table. We're not using lookup tables, we're using the visualize package to visualize the area under the curve, and that's what we're doing here. We're testing two-sided, which means that I not only have to put in my found t statistic of 1.9, but I also have to put in the negative value of that. Oh, sorry, yeah. So I also have to put in the negative value of that, the minus t, and I have to specify for this null distribution that it's based on a certain amount of degrees of freedom. So I already defined the degrees of freedom, which is n minus 1 here. And so this part, the number of degrees of freedom, determines what the t distribution looks like. So if you have a small amount of degrees of freedom, so essentially have a small sample size, you will get fatter tails, and if you have high degrees of freedom, it will be shallower at the ends. So you define this in the visualize function, and you have to specify that you will test two-sided. So you want it on both sides. The section should be tails. So if we apply this, then we find this distribution. So this is a student t distribution for this amount of degrees of freedom. So this is what it looks like. You can see that it has a mean of 0 and steps of 1, 2, 3, 4, etc. And the area, so what is the blue area here? What is the blue area that we're looking at?
The p-value?
Exactly, it's the p-value. And if we look at this p-value, for example, here, this point, what is this point called? What is this?
The critical value.
The critical value, I hear. Who agrees? Who does not agree?
Well, it was something with critical. Not sure whether critical zone or critical value.
Anyone else?
Maybe the critical threshold or something?
The critical threshold, I hear.
Or maybe I made that up, I don't know.
I find it very creative. Anyone else? So this is very good that I asked this question, and I see someone in the chat who has the correct answer. It's your found test statistic. It's just your t. It's not a critical value. It's your t value that you have found from your data. So that's exactly what it is. So you see, and that's a bit of a something that you have to work on, is that all these different terms tend to intertwine. So we have an area where which we define on the type 1 error, and that's associated with a critical value, but the t value is also a probability, so it also has an n. So is that this is not the critical value, this is just a t value. So try to describe the terms that we use, and try to really get the notion in on what the meaning is of these different parts.
Sorry, can I ask a question?
Of course.
Would the critical value then be the t value at which you would reject the null hypothesis from?
That's absolutely true. Yeah.
Okay, thank you.
So let's elaborate on this. So, what are we missing in this graph, in this plot? What is not showing?
Alpha.
Exactly, we're not seeing alpha. So the visualize function only displays the found test statistic or more extreme. So it's the p-value that you see in the blue areas, but we don't see alpha here. So if you would so let's go back to the relation between alpha and the critical value. So the if you choose an alpha of 5%, the critical value is at the point where you have the 5% under the curve. So if you have 5% and the end of that area, that is where the critical value resides. So the critical t-value on which on one side you reject the null, and at the other side you tend to not reject the null. So where in this graph would you draw that critical value? Let's for example, let's assume
but the x value is the number of standard deviations, right?
Yeah, but you don't have to. It's not that difficult. It's not a matter of calculation. It's a matter of conceptual understanding. So if we would choose an alpha here, we have to realize that we have that we are testing two-sided. So we have 2.5% on one side and 2.5% on the other side. Right? So where would the threshold, the critical value, where would it be? Would it be inside?
You would want less blue visible, so effectively you'd be taking that dotted line further out towards the tails.
Okay, so I think your conceptual understanding is good, but it's a bit dangerous because you're suggesting that we pull our actual found t value and therefore our blue area to the right, which would change our essentially the p-value that we found. So we have to dissociate the p-value that we find. So this is the p-value that we see here, and it's associated with the found test statistics. We'll leave that alone. So we'll imagine another area which would be red overlaying on top of this, and then you would say that area would be more to the right.
Yeah.
Okay. And why would you assume that? What is your reasoning behind this?
Because then you want the area under the line to add up to 0.05 or less to be critical.
Yeah, that's true, but we're absolutely true, but we're doing two-sided. So
for each side 0.025.
Yeah, exactly. So if you look at the area that we actually found on our t-statistic and the p-value, that's 0.06. So it's higher than 5%. So even if we would test one-sided, would be to the right of this, because the area would be smaller, because 0.05 is smaller than 0.06. Right? Are you following me?
Yep.
Is this
because we're testing two-sided, it would be even half of that. So you would have 2.5% somewhere. I think I would eyeball it somewhere here, and also on the other side.
Is the 0.06 not a combination between both sides of the tail?
Yeah.
So
that's a good point. Yeah, that's a good point that you're making. Exactly. That's true.
Do we divide that p-value by 2 again?
If you would test one-sided, you would, but now we're testing two-sided. So we have to find out what the relation is for the what our estimation of alpha would be for two-sided. So we'll keep it at two-sided for now because it's hard enough. But your remark is absolutely right. We have 6%. 6% on divided on both sides. So you have about 3-ish% on this blue area, and we have 3-ish% on this blue area. So if we would want 2.5% for the alpha, it would be a little bit to the right of this. So the red alpha area would be slightly to the right, and therefore we would refute our null or not?
We would reject it.
Exactly. And we can easily see that we don't need these kinds of graphs to make that interpretation, because we can simply see our p-value up here. It's higher than 5%. So we reject the null. Period.
I'm sorry, I don't understand. Why would you reject the null if it's when the p?
Sorry, you don't reject the null. I'm saying it wrong. Yeah. my brain is fried. We need coffee. Okay. Well, I'll stop. We're gonna get coffee. We'll start at 10 minutes before. 10 before half. I'm saying that absolutely wrong. I need coffee. You too? Are you all ready for coffee?
Yes.
Good. See you in a bit. So, I have my coffee. That means I can think again. Let's see. Can you still hear me? Always check if I'm not talking into the void. So, it's a good thing that we are concluding that our null hypothesis is true, that there's nothing going on, that in essence our narcissism in our student population is not that high, and so I think that's a good point at this point. So we'll go into this the alpha and determining the conclusion again in the independent sample t-test. But for now, we have to realize that we're not done yet. We need to know if this found t-value is actually large or not. So we have to make the translation from our actual t-value to our effect size. So in the final step in performing the paired sample t-test, we have to apply the effect size calculation, which essentially uses only the squared t-value and the degrees of freedom, the sample size, to determine the amount of effect size that we have, which we define in terms of this R value.
Can I ask a question?
Yeah.
Just going back to the graph in the previous slide. So we kind of concluded our critical value based on the p-value for the t that we had.
Yeah.
That's what we did?
Exactly.
Thing? Okay, that was just to be sure, because I was a bit confused how we concluded the critical value. So
yeah, no. So what you're saying, you concluded what your p-value is based on our critical value. Based on our found test statistic. That was this one. This line, what I'm showing here, that's the t-value that we found. This is the p-value associated with this, the area under the curve. I have this on the right side and on the left side. The total probability of having such a value or more extreme, and extreme being to the outskirts on the right and on the left, this probability is 0.06, so 6%. And our alpha level of 5% should be 2.5% on this side, which we don't see here, and 2.5 on this side, but 2.5 is together on left and right is 5%, and we see that we have 6% here. So our found p-value is higher than the 5% that we would use as our threshold. Does that make sense?
Yes, thank you.
Good, very good. It's no problem you ask these questions. It's very important you have this clear and can make the distinctions between these two.
There is a question in the chat.
Okay.
Why would you calculate the effect size if the results are not significant?
Because what we talked, it's because exactly the point that we talked about earlier. We do not know what the actual alternative distribution would look like. We don't know if the actual effect would be high. So, and because we are talking about the probability in the long run, this result that we found here could be one of those. Let me phrase it differently. We could also be wrong about this conclusion. That makes sense, right?
Yes.
So what we actually need is, if you do replications, you need all effect sizes to make an estimation of what the actual alternative distribution would be. So what the parameter of the alternative distribution would be. So what the mu of the alternative would look like. And for that, I need all effect sizes, because if I would only use the effect sizes for those where I would have found an effect, for those where I would reject the null, then I'm actually blinding myself. I'm basing the assumption on where the alternative distribution would be only on a limited set. So even if you don't find a significant result, it's still important to also write down the effect size so that meta-analysis can use this information. And we have a big problem in research and psychology in that, because you've probably heard of this file drawer effect, where if you don't find significant results on your research, it just doesn't get published. So we have a very skewed view on what is actually going on in the world. And well, this whole replication crisis that we are in at this moment shows us that we in the past in the 1960s, and there has been a lot of research done where the conclusions on one experiment has been taken as if this really was the thing that was going on, and years of research that have been built upon those notions upon those findings assume that those experiments that have been done in the 60s and 70s were actually true. But what we're finding now is that while we're spending time to replicate those studies, we can't find the same effects. It was a fluke. And that happens since the fundamental of statistics governs the fact that your result that you find in your one research finding could be a fluke. If you reject the null in 5% of the times, you reject it on a false basis because it's not true. So what we're seeing now is that there's more also money being spent on trying to replicate studies and having a more thorough understanding of what is actually going on. And this requires us to not only publish research where we find a significant result, but also where it doesn't, and we also need to report the effect size on those measures. So, well, that was a rant. Okay. Does that make sense?
It's not quite clear to me why we calculate the effect size, like what that is.
Yeah, so the effect size is essentially the difference. Well, if you look at what we're showing here, we use the t-value, and this whole formula is just to standardize this value so we can compare it to other effect size measures. So
could you share your screen again?
Oh,
please?
sorry. Yeah. So this effect size calculation that we do here, it's just to standardize, so we can compare it to other effect size measures. But if we look what the content of this thing is, it's actually the found test statistic. It's the main ingredient here. So our effect size here is determined, and that is also in line with what we talked about last week. It's in line with this whole post hoc notion. It's not the real effect size between the null distribution and the mu of null and the mu of the alternative distribution. No, we're assuming and we're defining our effect size as the effect size based on the null, where we would assume nothing going on, and our actually found test statistic here. So it's essentially this distance, what we are reporting. And if I would replicate this study next year and the year after that, the found test statistic might vary. Sometimes it might be very significant, and if that on an overwhelmingly a frequent basis, if I would go on for 100 years, and only 5% of the time it would be on this side, and the other 95 on the other side, then reporting those effect size measures will give us a very good notion of the position of the actual mu of the alternative. So that's why we need this.
For the test, if we have problems filling this formula into R, can we also use a normal calculator? Because that's what I did with one of the WAs.
Oh, we actually want you to use R, so I would urge you to use.
To upload the R or SPSS things for the test.
No. So we can't really check that, right?
Well, if you upload it, I don't know if.
Yeah, no, I'm not gonna ask you to upload those texts, because then I have to check it, and I don't have time for that. Okay. One more thing, and then we'll go into the independent sample t-test, and that is what we've been doing with this with the t-test for paired samples is actually creating a new vector, the difference vector, and then using that as the basis for our t-test. But what we would like to see if you would report on the results, if you would find a significant difference or not or whatever, you would have to phrase that, write that down in your article, in your report, in terms of we didn't find a significant difference between the pre-test and the post-test, and or we did, but it would be described in terms of finding or not finding a significant difference between the pre-test and the post-test. And that brings us a little bit to an issue where because we would also like in some journals and papers to visualize this effect. So instead of just writing it down, you would probably want some bar chart indicating the difference, but also applying the confidence intervals. And SPSS, by default, if you select a column and you ask for the confidence intervals, it bases that column, the confidence interval it bases that on the data only in that column. But our data is essentially related because we have a pre-test and a post-test, and also for our pre-test and our post-test, our assumption of the null would be that those difference that there wouldn't be a difference. So we're looking at the difference score. So if you would go the standard SPSS route, that would mean that the confidence intervals would be exaggerated. And that poses a problem because if the confidence intervals that you're showing do not relate to your actual test that you've done, because if we, for example, find a significant test of a significant difference between the pre-test and the post-test, and we show that in a graph, and our error bars overlap wildly, then someone would question your analysis, because you're saying that there's a significant difference, but if I'm looking at the error bars, they overlap wildly. And that is because SPSS does not correct for the fact that you are doing repeated measures. Field has in the book a chapter on this topic, where you actually need to correct your observed columns for the fact that you're doing repeated measures. And what I'm showing here is essentially the SPSS code that you would need, where you apply this adjustment measure. And while applying this adjustment measure, you create essentially a new variable which is corrected for the fact that for the overestimation of the confidence interval. And if you do that, you can use those measures and then run SPSS to ask SPSS to perform a regular confidence interval. And only if you do that, your confidence interval will represent what you're actually doing in your test, and they will be smaller, and you would see that in your data. So I actually had a student email me at one time where he already did the SSR course and was in year 4 in the study, and he went to a conference, and then he heard someone say that that they had found a significant result, but and he emailed me a picture of the confidence interval that overlapped, and said, here's what's going wrong, and this is what you have to do to correct that. So try to do that in the assignment also, and see it not just as a conceptual correction for this confidence interval, but see it also as an extra some extra practice to use the compute function in SPSS, and just try to look at what's going on here and try to see if you can get to the same thing in SPSS as me. Okay.
I'm sorry, will this also be explained in the weekly assignment perhaps? Like or do we have to paste the syntax, or are
I think it's in the weekly assignment going through these steps. So
okay, great.
But it's good to see what the steps are, and to see if you can relate to this.
Okay, yeah. Thank you.
Yeah.
Do you have to do this every time you're performing your repeated measures?
It depends. If you just want to do a repeated measure to see if there's a difference or not, and for your studies or some arbitrary analysis, then it's not really needed. But if you're going to publish, if you want to have a graph showing the differences in your paper, well, then you have to apply this, because otherwise your graphs will be an incorrect representation of what's going on.
Okay, got
Yeah.
it. Thank you.
You're welcome.
So we should learn all those codes by heart, or can
No, no, absolutely not. No. No. That's a relief, right?
Yes.
Yeah, okay. I'm not sadistic. Come on.
Ha 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 ha.
The independent sample t-test. Here we go. So the independent sample t-test we use for two independent groups. And what I want you to do is look at this formula for a second and then explain to me how this relates to the previous one.
In the previous formula, we also subtracted the means, but in that formula, it was the means of the pre and the post test. And in this formula, it's the means of the different groups you are comparing.
Exactly. So in our previous example, so with the paired sample, we didn't subtract the means, right? We said we subtracted the actual scores for each individual to create a new variable, which we called D, and from that variable, D, we calculated the mean, and we used that to compare to our mu of the null. And here, we're just saying, well, we have two groups. They're independent. So this could be a gender as a grouping variable, where we have a mean in one group and we have a mean in the other group, and we're subtracting those two. So that's absolutely correct. So the thing I want you to see is that we're doing essentially again the same thing. We are calculating some difference, some mean, some sample mean from our data. We're comparing it to our specified mu, where if in the notion of when comparing two means, then you would assume under the null that there won't be any difference. So the mu you would set to 0, and you just divide by the standard error, and that will yield you your t-value. That makes sense, right? Do you see that we're doing the same thing again?
Yes.
Okay, very good. One thing that is different here is that we do have our standard error, but we see it's the standard error of p. And we will look into this because we're using the two samples, for example. In our case, we have two independent samples, and somehow we need to combine those two to get a standard error of the combination of both. And we have to think about how we'll look at how that will take place. So our t can be 0, which should be equal to mu for that t, which we expect. We have some alternatives. Again, here you could specify this in a different way. You could say mean x1 is equal to mean x2, or well, you could find different ways in formulating this null and alternative hypothesis, and we talked about this already. Oh yeah. So before I go to the next slide, so how does this look in SPSS? What does this look like? What do we have for columns and rows and such?
You'd have a column, I think, which would be groups, and then either 1 or 2. So the test subject would either fall into group 1 or group 2.
Exactly. Anything else? So what you're saying is you would have a column representing essentially the independent variable, where in the cells you specify the levels, which would only have 2 levels because it's still a t-test, which can only handle 2. What more do we have in SPSS? Anyone else?
The scores.
Exactly, the scores.
Subjects. And that's one column.
That's another column.
Yeah.
Yeah. So
it's 2 columns.
It would have still 2 columns, but in this case, one of those columns represents the grouping variable, so the independent variable with levels, and we would have an outcome column, so the dependent variable, which would contain the data for this for these results. You can see it here. You have the grouping variable, which is the independent one with level 1 and level 2, and the outcome. Make sense?
Yes.
Cool. Now we have some additional assumptions.
Right. What was K?
What was?
K.
K is the independent variable, and the K stands for the levels that we have. It has K levels, and a t-test has only 2 levels, so K is equal to 2. I'm using K specifically because later on in the course and later on in the formulas that we will be using, K is used as being a representation of the level of the amount of levels that we have.
So in this case, since there are 2 groups,
yeah,
that's why there's 1 and 2.
Yeah, and it's always 2 groups with a t-test, because if you would have more, you can't do more in a t-test.
Yeah.
Though in SPSS you could have, for example, a placebo group and an experimental group and maybe another experimental group. So you would have 3 levels, and then you have to realize that you can't use the independent t-test for comparing those 2, but you could, for comparing those 3, but you could compare 2. So you could specify in SPSS, I only want to compare group 1 with 2, or I only want to compare group 1 with 3. So those kinds of options are provided in SPSS, but we'll go into that later. Now there are some assumptions that we have to check, and we haven't come across a lot of assumptions up till now, but at the point where we're going into comparing different groups, we have to apply and test our assumptions. And for the independent sample t-test, our assumption is that the variances of both groups should be equal. Is there anyone who could explain why we would have such an assumption? Why do we need such an assumption? Anyone?
Because we want it to be part of the same population.
Exactly. And why do we want it to be part of the same population?
Because at the end we want to be able to say something about the population based off of our experiments, our tests.
Yeah.
So
go ahead.
So if we're testing from 2 different populations, then it wouldn't really give us the conclusion that we're looking for, where we can say something about a population because we're testing 2 different populations.
Yeah, but you could go for the argument that if there's a difference, if there's actually a difference in between our 2 samples, because for example, males and females actually differ in their average muscle mass, for example, then you could argue that those are actually different populations.
Yes, but if they're not from the same population, then there are too many other variables that could contribute to the difference that we're seeing.
Okay.
Rather than our independent variable.
Yeah. Has anyone else have different thoughts about this?
Well, I would agree with her in terms of like we want to find the difference within the conditions, not necessarily within the population. Like we want to have the same population with like equal variance, and then within the different categories, we put them. We want to find the difference.
Yeah. So I'm gonna prime you now a bit. We are basing our conclusions to reject or not reject on the assumption that the null hypothesis is true. So we are assuming the null to be true, and in this light, how would you view the assumption of equality of variance in this light, under the notion that we assume the null to be true?
So under the null, the random variance would be equal, whereas
Exactly.
under the alternative, there would be a systemic variance. So we would just find the difference between the random variance and the systemic difference.
Exactly. That's absolutely the case. Very good. We are assuming the null, and if you sample from that same null, then, well, obviously, your two groups that you would sample from that null would have would need the same variance. If that's not the case, then that would have some implications on our on the conclusions that we take based on our assumptions. So that is why we do these assumption checks for these kinds of tests.
Can I ask something?
Yes, of course.
When we say the same variance, do we mean exactly the same or about the same?
We're testing again. So if you see, we apply in SPSS a test, a statistical test again. So we're doing the same null hypothesis testing, only on the variance this time. So it's not exactly the same. It's about the same. More specifically, we actually want to see the null for this assumption to be true, right? So the null assumption would assume no variance, and in 95% of the times you would find that. So we actually want to find a p-value higher than 0.05, than 5%. So we do not reject the null of the variance so for the variance to be equal. So it's not exactly, it's approximately, it's statistically, so we can test it. Yes. And we do this in SPSS. When you run this analysis in SPSS, it also gives you the test of equality of variance.
Okay, thank you.
Yeah, very good. For our example, I will, in this case, will generate some random results, namely males and females. And I will add that to the data that we already had. What are your assumptions on this? Will there be a difference in the IQ estimates? We're using the IQ estimates to collect it. Yeah, and do you think there will be a difference between males and females if I do this?
No.
No, why? Why do you think they won't differ? Anyone else?
I just wonder why. Sorry.
No, go ahead.
I mean, why should they differ?
Do they? Of course.
I think they might differ because I think there might be a difference as to the perceptions of males and females to their neighbor.
Okay, that could be true. But what I'm doing here now is randomly creating males and females. And so I'm simulating this, just getting a bunch of gender categories and applying this to the data. So I just create a few, and this will the estimation of your own IQ for males and females. So because this is just randomly generated, it should not show any results because I've randomly applied them to this data set. So in reality, you could have an argument, but because I'm randomly assigning, this should not yield significant results. Do you get that?
That depends on the n, right? How many people you have used for this experiment.
No.
Because now with 8 people, there might be, because of chance, like there could be a difference.
Yeah, there are more than 8. There are more. But of course, there could be a difference, but I randomly assign, so there's nothing structurally in there which would indicate that there should be a difference. So in terms of thinking about null hypothesis testing, this is a random process. So if we would find a difference here, it would be it would indicate our 5% fluke that we talked about earlier. So we absolutely know that there should not be a difference because we randomly assigned it, but there could, of course.
That also means that was the reason why the variance should be the same, because the chance of finding a male with an IQ of 125 is the same as a female with an IQ of the same. So that's why the variance should be okay. All right, clear.
Was that the IQ that they thought they had, or the IQ that they actually had, or is this what they imagined that they had?
Yeah, the question was what is your IQ and what is the IQ next to you? So this is of course a difficult topic, right? Because maybe you actually know what your IQ is and you write it down, or maybe you have no idea and you write something down, or maybe you know what your IQ is but you think, well, I'm gonna put myself down as being smarter or not. Well, okay, let's not get into that.
Okay, not important now.
No. So for the example, to do the calculations, we need the means for the males and for the females. We can calculate this. We see 121 and 118. We also need the variance for both. And we need the sample size. So with those parts, we can actually calculate the t-value. And this looks a bit daunting, and it is in a sense, because doing the top above is quite easy. We can just say, well, what's the difference between the mean from the 1 and the mean from the 2, and we subtract the mu from that. But we have to use the standard error of both groups. So we have to pull these the standard errors together, and for that we have to get to the pooled standard errors. We have to apply the variance, the combined variance, and subtract the sample size for one group and the other group, which this is not that hard, but we need to get to the combined variance, and that's a bit of a, well, it's a lot. Let's leave it at that. But it's not that difficult to implement. So what we're doing to get the pooled variance is we have to essentially n-1. What was that again? How do we, because I haven't defined this in terms of a name, but how would we call n-1? Exactly. Anyone?
Degrees of freedom.
Yeah, exactly. It's the degrees of freedom. So we have to multiply the degrees of freedom by the variance of one of the first group, and we have to add the multiplication of the degrees of freedom by the variance of the other group, and divide that by the total degrees of freedom of the both groups combined, and that is, of course, adding both groups sample sizes, and in this case, because we have two groups, subtracting with 2. So if we do that, we have all the ingredients that we need. So we'll go through that quickly. So applying this would mean first determining your degrees of freedom for the lower part, what I do here, So I have the n for one group, I have the n for the other group, and I subtract 2. That's the degrees of freedom. And I have the pooled variance, where I have the degrees of freedom for one group, well, spelled out essentially, multiplied by the variance for the other group, and do the same thing for the other group, and essentially divide this by the total degrees of freedom, which will yield me the actual degrees of freedom, which will actually get me to the pooled variance. So we have to go through these steps. It's a bit of a nag to get through. And then apply it to get to the actual standard error, the pooled standard error. So we apply this value, the pooled variance, to both groups, and calculate, that's what I did here, and calculate the actual standard error. And now that we have this, now we can use that to calculate the t-value, and the final step here is essentially the same as we did earlier. We look at the difference, we subtract the mu, that is 0, and we divide by the standard error. Doing this will result in a t-value of a 1.4. Do you think that this is a significant t-value?
Well, I would say no, but of course it depends on the degrees of freedom.
Okay, you say you think you would say no, but it depends on the degrees of freedom. Is there anyone else who is not so hesitant about the degrees of freedom?
I think this might always be too low.
I think so too. Because we've seen the different forms the t distribution can make. We have seen how it looks like with 5 degrees of freedom, but we've also seen how it looks like with 10 degrees of freedom. We've seen that it always fades out at point 4. It's almost flat, and we've discussed earlier that around 2 we're not sure, but being 1.4, well, this is very close to so I think I would put my hand in the fire for this. I don't know, is that a good expression in English? I don't know. In Dutch it is. Okay.
No.
Well, thanks for that. Okay, so we're gonna test it. That's a good thing to do always. We're gonna test two-sided again. We apply the same visualize function, and we will see that our p-value left and right combined is equal to 0.16 we find here. So that's higher than if we would have a critical value based on an alpha of 0.5. So this means this 0.16 means that we have an area of 8% underneath this, the right side, and we have an area of 8% under the left side. If we would use an alpha of 5%, it would mean 2.5% on this side, well, which would be somewhere around here-ish, and 2.5% on this side. We can see that if we would have had that alpha of 2.5% there, then our critical value would be at such a p-value here, such a t-value here on the x-axis, and we see that our t-value that we found exceeds that. We can also clearly see that this area is very large, so there are multiple views on which you can conclude that there's nothing going on here, and that we will not refute our null hypothesis.
Can I just ask something?
Yeah, of course.
I seem to remember that with an alpha of 0.05, there comes a t-value of 1.96, right?
No, that's I understand where that comes from. This comes from the standard normal distribution. So because the standard normal distribution, the distribution is always the same, we know that 95 confidence interval is associated with a value on the x-axis of exactly what you said. But because the the t distribution varies based on the degrees of freedom, there's not an exact value which is always the same where the 5% holds. It differs because the distribution is sometimes a bit fatter at the tail. So you don't have an exact value where you can always say this is the place where the critical value is for 5%. And that's because the distribution changes a bit based on the degrees of freedom.
Yeah, makes sense. Cool. There's also a question in the chat saying the slides posted on Canvas show a different t-value. Is that correct?
That could be because I updated my slides here today, and I actually used the data that people fill in. So if if it's not the same timing, then there could be a slight difference in the results. So that could be. But the concept is still the same. Okay? Effect size, same way. And we're ending on that. You ready to stop? I am.
Thank you.
You're welcome. I'll be sticking
you.
around. I'll be sticking around for some questions if there are, and good luck with the last weekly assignment. Good luck with the preparation for the exam, and some extra SPSS support we will discuss through the tutorials. Thank you. See you next time.
Thanks. Bye.